June 1944, Normandy, France. The rain had not stopped for 2 days. The fields were mud, the roads were rivers, and every bridge the Allies needed to cross had been reduced to twisted wreckage by retreating German engineers. Yet, as the first grey light of dawn crept over the hedgerows, American soldiers were already driving trucks and tanks across a new span that hadn't existed the night before. Built from hundreds of identical steel panels, each one carried by hand, the bridge stretched cleanly across the flooded river. From a distance, it looked almost impossible, a fully functioning structure rising overnight out of chaos. Observers from the German side could scarcely believe it. One Japanese liaison officer assigned to study German engineering units recorded in his notes, "The Americans are using a system we do not understand. They build as if the steel itself obeys them." That image, men assembling a bridge in the dark, under fire, without cranes or heavy machinery, would travel across continents and survive long after the war ended. The Allies called it the Bailey Bridge, named after its British inventor, Donald Bailey. It was not a weapon in the traditional sense, it fired no shells, it destroyed nothing, yet it gave armies the one thing wars are always fought over: movement. The ability to advance, to cross, to rebuild faster than the enemy could destroy. To the Japanese engineers who examined its blueprints years later, it was more than technology. It was a revelation, proof that victory could be manufactured, piece by piece, on an assembly line. In their post-war reports, they described it with a phrase that seemed almost poetic: the weapon disguised as a bridge. The story of that bridge begins in Britain, for years before D-Day. The story of the Bailey Bridge began not on a battlefield, but in a modest engineering office in London in 1940. Britain was reeling from the Blitz, and the threat of German invasion loomed over every discussion in Whitehall. Across the English Channel, Nazi forces had demonstrated an unprecedented level of mobility, tanks and mechanized columns sweeping through France in weeks. The British Army understood that the next war would not be won by static fortifications or heroic defenses, but by speed, the ability to move men and armor as quickly as the enemy. In this atmosphere of urgency, Donald Coleman Bailey, a civil engineer with the Ministry of Supply, began experimenting with model bridge structures made of meccano parts at his kitchen table. Bailey was not a general or an industrial magnate, he was a quiet, methodical designer who believed in solving complex problems through simplicity. What he envisioned was a modular bridge system that could be assembled from standardized steel panels, interchangeable parts that required no special tools, no cranes, and minimal training. His early prototypes were built and tested at the experimental bridging establishment in Christchurch, Hampshire. The key to Bailey's design was its modular truss system, a rectangular steel panel with diagonal bracing that could be pinned together horizontally or vertically to create longer and stronger spans. Each panel weighed about 570 pounds, light enough for 6 men to carry, strong enough to bear the weight of a tank once assembled in multiples. The genius of the system lay in its scalability. Engineers could adapt the same components to build short footbridges or 200-foot tank crossings by simply adding more panels and reinforcing sections. By 1941, the design had passed its first rigorous tests. The British Army approved production under strict secrecy, assigning it the designation Bailey Bridge, portable, prefabricated. Early manufacturing began at the Cleveland Bridge and Engineering Company, and within months, the first shipments were sent to North Africa for field trials. The initial deployments during the Tunisia campaign in 1942 were a revelation. Under enemy fire, Royal Engineers erected a 120-foot Bailey span in just 9 hours, allowing tanks of the 8th Army to cross wadis that had stalled operations for days. Commanders quickly realized the system's value. A single train car loaded with panels could replace weeks of construction effort. The design was soon standardized across the Allied forces. Canada, with its vast industrial capacity, became a major producer of Bailey components, while the United States adopted the system in 1943. American engineers studied British assembly manuals and immediately recognized its potential. The U.S. Army Corps of Engineers began integrating Bailey sections into training programs, developing techniques like the launching nose, where assembled spans were pushed forward on rollers over rivers using a projecting lightweight frame. This method allowed entire bridges to be built on one bank, then launched across gaps under enemy fire without exposing men directly to danger. The system's modularity fit perfectly with the American logistical mindset: standardized, efficient, and fast. Each Bailey kit was catalogued, numbered, and pre-packed for transport. Panels were interchangeable between British, Canadian, and American units, a level of standardization that astonished even seasoned logisticians. It meant that a bridge destroyed in France could be rebuilt using spare parts made in Detroit or Montreal. For Japanese military observers attached to the German High Command, this represented a new dimension of warfare. Japanese engineers were deeply skilled in traditional construction. They could design dams, rail lines, and tunnels, but their wartime industry lacked the mass production and interchangeable part philosophy that defined Allied logistics. Their bridge building relied on labor-intensive methods using timber or fixed steel trusses, often requiring days or weeks to complete a single crossing. In Burma, where monsoon rains turned rivers into torrents overnight, Japanese field engineers frequently had to rebuild bridges using bamboo and local materials. Their systems were ingenious but fragile, and without motorized transport or standard equipment, progress was slow. The concept of a bridge that could be carried in pieces by truck and assembled by untrained soldiers was almost beyond comprehension. Bailey's design changed the very definition of what an army could do. A military bridge was no longer a static structure, it became a mobile weapon of logistics, an instrument that extended operational reach. The British Army used to say, "Infantry wins battles, engineers win wars." The Bailey Bridge embodied that philosophy. By the time of Operation Overlord in 1944, the Allies had produced more than 500,000 tons of Bailey components. Each D-Day beachhead was supplied with pre-packaged bridge units, stacked neatly in crates, ready for rapid deployment. Within 24 hours of landing, Allied engineers were erecting Bailey bridges over the flooded Norman countryside, ensuring that tanks, artillery, and supplied trucks could keep pace with the front line. Meanwhile, in Tokyo, the Japanese Army Engineering Bureau maintained a small liaison office that analyzed foreign technical intelligence. Reports coming from Berlin described the remarkable speed of Allied engineering operations. Some of these reports referenced the British portable bridge, noting its modular steel frame and unusual method of launching. But the details were incomplete, and Japan's industrial base was already strained by shortages of steel and fuel. They noted the bridge, but underestimated its importance. Only after the war, when Japan was permitted to examine captured Allied documentation, did the scale of the achievement become clear. To those engineers, the Bailey Bridge represented not just clever design but an entirely new way of thinking, a system where every piece, every bolt, every pin was part of a greater industrial symphony. It was, as one post-war Japanese report described, a structure born of a civilization that had learned to make even its bridges by machine. The bridge's origins were humble, its inventor unassuming. Yet the world it was built for, a world defined by total war, turned that simplicity into power. By 1943, the Bailey Bridge was no longer a prototype confined to British testing grounds. it had become an industrial campaign in itself. Britain, Canada, and the United States were producing panels, transoms, and decking at an extraordinary scale. Factories that once built locomotives or farm machinery were repurposed to forge Bailey components around the clock. The British Ministry of Supply coordinated over 650 subcontractors, each manufacturing standardized pieces with tolerances so precise that any panel, from any factory, could fit into any bridge built anywhere in the world. It was an early triumph of what modern historians call interoperability, a logistics revolution hidden beneath layers of steel. The panels were designed for rapid transport. Each section measured 10 feet long and weighed roughly 570 pounds. Soldiers learned to carry them in pairs, each man gripping a handle as if lifting a stretcher. Pins and bolts were standardized in labeled crates, the parts stamped with letters and numbers for field identification. What had once been a laborious engineering challenge now resembled a construction kit, a system that turned road repair into assembly rather than improvisation. As Allied planning intensified for the invasion of Europe, the Bailey system became indispensable. The Allied command in London predicted that nearly every river, canal, and culvert in France would be demolished by retreating German engineers. The Transportation Corps warned that without an immediate means of rebuilding, the advance would stall within days. To prevent that, entire units of the U.S. Army Corps of Engineers, Royal Engineers, and Canadian military engineers trained exclusively on Bailey assembly throughout 1943. They built bridges across English rivers, the Avon, the Test, the Itchen, again and again, breaking them down and rebuilding them to improve speed. At Salisbury Plain, teams of engineers competed to set records. The fastest could erect a 150-foot double-truss Bailey span in under 6 hours. These exercises became almost ritualistic, the rhythmic hammering of steel pins, shouted orders timed with stopwatches, the moment when the final decking planks were laid and a jeep rolled across to cheers from the men. Among those who witnessed the training were visiting officers from Allied nations, including a small number of German defectors working with British intelligence. The reports that filtered back to occupied Europe painted a daunting picture. The Allies were not only preparing armies but mastering logistics at an industrial tempo never seen before. For the Axis, who relied on slower, less standardized methods, the implications were profound. When Operation Husky, the invasion of Sicily, began in July 1943, Bailey bridges made their first large-scale combat debut. The rugged Sicilian terrain was a nightmare for transport, destroyed viaducts, craters, and deep ravines cut supply routes every few miles. Within 48 hours of landing, British engineers erected Bailey spans over the Somato and Detano rivers, restoring the mobility of the Eighth Army. Field commanders noted that the bridges performed flawlessly under the weight of Sherman tanks and heavy transport vehicles. The Times of London later called it the bridge that followed the army. Encouraged by success, the Allies expanded production further in preparation for the liberation of mainland Europe. The Americans took the British concept and applied their own scale of logistics. The U.S. Steel Corporation, Inland Steel, an American bridge company began producing thousands of panels per week, each conforming exactly to British specifications. Massive stockpiles were assembled in depots across southern England, neat rows of trusses, beams, and decking, labelled for easy transport. It was, in every sense, industrial warfare in its purest form. When D-Day finally came on June 6, 1944, Bailey components landed on the beaches of Normandy alongside ammunition and rations. Within 24 hours, the first Bailey Bridge in France, a 100-foot span across the river Via near Saint-Lô, was operational. Its completion marked the beginning of a new phase of mobile warfare. From that point onward, the Allied advance became inseparable from the metallic rhythm of Bailey construction. Every major river crossing across Europe bore the imprint of Bailey ingenuity. In France, Belgium, and the Netherlands, photographs captured endless convoys of trucks carrying bridge parts stacked like latticework. The bridges were classified by military load class, ranging from Class 40, capable of supporting medium tanks and transport vehicles, to Class 70, for heavy armor and artillery. Engineers learned to strengthen structures by doubling or tripling the trusses, stacking multiple layers of panels to increase load-bearing capacity. The genius of the Bailey system wasn't just its strength, it was its adaptability. The same components could be rearranged to form a floating bridge using pontoons, or a high-level crossing supported by steel piers. In Italy, where mountainous terrain created deep river gorges, engineers built multispan Baileys suspended on scaffolding towers. Each configuration had its own nickname: single-single, double-single, double-double, denoting the number of trusses used. The terminology became second nature to every engineer from London to Los Angeles. What had begun as one man's tabletop experiment had evolved into a weapon of mobility. Donald Bailey's creation now served not only as a structure but as a doctrine, a way of thinking that valued modularity, repetition, and precision over improvisation. Each bridge completed was both a victory of design and a testament to organization. To the soldiers who built them, the work was grueling. They carried steel through mud, under fire, often in freezing rain. Many engineers died in the process, their names rarely recorded in the official histories. Yet every bridge completed kept armies moving, a silent triumph repeated hundreds of times across Europe. By late 1944, as Allied forces reached the Siegfried Line, Bailey bridges had become so common that German units began referring to them in their own reports. One Wehrmacht engineer's diary recovered after the war contained a single, bitter line: "They build faster than we can destroy." That, more than any tank or bomber, defined the logistical supremacy of the Allies. As the Allied armies pushed deeper into occupied Europe, the Bailey Bridge reached its ultimate proving ground, the rivers and canals of France, Belgium, and Germany. Every retreating German unit followed a scorched earth policy, demolishing bridges and roads to slow the advance. What they didn't anticipate was how swiftly the Allies could rebuild them. With every destroyed span came an opportunity for the Bailey to demonstrate its value again and again. In late August 1944, as General Patton's Third Army raced across France, supply lines began to stretch dangerously thin. The bridges across the Seine had all been destroyed, and aerial reconnaissance showed no intact crossings within 50 miles. Engineers from the 249th Engineer Combat Battalion were given a near-impossible order: construct a bridge across the Seine near Mantes-Gassecourt before sunrise, or risk halting the advance. Working under artillery fire, 276 engineers began assembling panels by moonlight. Trucks rolled forward with pre-packed crates labeled A1 decking, B2 panels, and P-pins. As the night deepened, the rhythmic clang of steel echoed across the riverbank. Floodlights from passing tanks illuminated the truss frames as soldiers hammered pins into place. By dawn, a 720-foot, triple-truss Class 40 Bailey Bridge, one of the longest built during the war, stood complete. Patton's tanks crossed before breakfast. The German defenders, expecting at least a 3-day delay, were overrun by noon. It was moments like this that cemented the bridge's legendary reputation. War correspondents began referring to it as the bridge that won the race to Berlin. The simplicity of its construction was its greatest strength. Unlike other military bridges that required engineers by trade, the Bailey could be built by regular soldiers trained for just a week. The structure needed no welding or cranes, only manpower, teamwork, and a sense of rhythm. Each Bailey Bridge followed a methodical choreography. First came the rollers, steel frames placed at the near bank to support the span during assembly. Then came the panels, pinned together into trusses that grew outward with each addition. Once a sufficient length was reached, a launching nose, a lightweight skeleton of panels, was attached to the front. The entire bridge was then pushed forward on rollers, inch by inch, across the gap. When the nose touched the far bank, the structure settled into place. Wooden decking was laid, curbstones bolted, and within hours, vehicles were rolling across. By the time Allied troops reached the Rhine River in early 1945, Bailey bridges had become the symbol of Allied momentum. The Rhine, wide and fast-flowing, was expected to delay operations for weeks. But in one of the most remarkable engineering efforts of the war, American and British units constructed multiple Bailey crossings in record time. Near Remagen, after seizing the Ludendorff Bridge, the last intact span over the Rhine, U.S. engineers began building parallel Bailey structures to secure the crossing before the captured bridge collapsed. Within 10 days, a new 1,000-foot Bailey Bridge stood beside the damaged Ludendorff span, carrying thousands of vehicles daily into Germany. These feats astonished even the Germans, who had prided themselves on technical mastery. Reports captured by Allied intelligence described the Bailey system with reluctant admiration. One translated field memorandum, found in a destroyed Wehrmacht depot, stated simply, "Enemy engineers possess a modular bridge that requires no cranes. They can cross any river in less than 1 day." Meanwhile, in the Pacific, Japanese intelligence officers stationed in Berlin were also taking notes. Through diplomatic and military exchanges, they obtained fragments of Allied technical data, including photographs of Bailey construction. The Japanese Army Engineering Bureau sent inquiries to its attachés in Europe, seeking blueprints or detailed specifications. By late 1944, a few incomplete sets of plans had reached Tokyo through German channels. But without access to Allied steel alloys or machine tooling, reproducing the bridge was impossible. Still, Japanese engineers studied the concept with fascination. In their notebooks, preserved today in Japan's National Institute for Defense Studies, they described the Bailey system as a bridge that flows like water. To them, it was not only a marvel of design but a symbol of a different kind of industrial civilization, one where efficiency was as powerful as firepower. As the war neared its end, the Bailey Bridge became an emblem of Allied cooperation. British design, Canadian manufacturing, American logistics, each nation contributed to a system that embodied shared ingenuity. General Eisenhower later described it as one of 3 decisive engineering innovations of the war, alongside radar and the landing craft. Without the Bailey Bridge, he wrote, we could not have won. By May 1945, more than 2,000 major Bailey bridges had been constructed in the European theater alone, spanning rivers, canals, and bomb craters across 12 countries. Many remained in service for decades after the war. In rural France and Italy, farmers continued to cross Bailey spans built by wartime engineers well into the 1970s. For the soldiers who built them, the bridges became a point of quiet pride, a symbol of what teamwork and discipline could achieve under fire. They often joked that the bridge fought the war without firing a shot. But to military historians and engineers, the Bailey Bridge represented something far more profound, the moment when industrial design became strategy, when logistics itself became a weapon. For the Japanese officers who studied its blueprints years later, that realization would strike with particular force. To them, it was evidence that the future of warfare belonged not to those who built bigger guns, but to those who built faster, smarter, and with precision. In the postwar years, they would give it a name that captured both awe and humility, Kikai no Mahu, or mechanical magic. By early 1945, the Bailey Bridge had become more than a tool of engineering. It was a symbol of unstoppable momentum. As the Allies closed in on the heart of Germany, rivers once thought to be natural barriers fell one after another beneath the weight of modular steel. But among all of these crossings, one moment stood apart: the struggle for the Rhine River, the last great obstacle before Berlin. In March 1945, reconnaissance aircraft photographed the Rhine's western bank lined with wreckage. The Germans had blown almost every bridge, believing that the wide, fast-moving river would delay any Allied crossing for weeks. But fate and engineering had other plans. On March 7, American forces of the 9th Armored Division discovered that the Ludendorff Bridge at Remagen still stood, its demolition charges having failed to detonate. In an instant, history turned. American infantry rushed across under artillery fire, securing a precarious foothold on the east bank. The bridge, though battered, began to sag dangerously from the strain of traffic and damage. It was then that U.S. Army engineers performed what many called a miracle of wartime construction. Working day and night under enemy bombardment, they began assembling 2 Bailey bridges to flank the collapsing Ludendorff span. Each structure required thousands of panels, trucked in from depots miles away. Soldiers worked knee-deep in mud as shells exploded around them, hammering pins and tightening bolts with raw hands. Floodlights turned the construction site into a target, but the work never stopped. Within 10 days, 2 fully operational Bailey bridges stretched across the Rhine, carrying tanks, trucks, and troops into Germany. The speed of the crossing stunned both sides. German officers monitoring radio reports described the feat as unthinkable. They had counted on the Rhine to hold for weeks; it held for just days. The Allied Rhine crossings, supported almost entirely by Bailey bridges and pontoon systems, became the clearest demonstration yet that logistics, not luck, would decide the war's outcome. Meanwhile, in Tokyo, far removed from the front, Japanese intelligence analysts pored over intercepted German dispatches describing the same event. The cables from Berlin spoke of rapid bridge assembly by hand, steel components fitted without cranes, and bridge launch by rolling mechanism. Engineers at Japan's Army Technical Bureau could hardly believe it. Their own wartime bridging systems, typically wooden trestles or field-built steel frames, required days of labor and heavy machinery. The idea that American soldiers could carry steel panels across a battlefield and assemble them overnight seemed fantastical. When translated into Japanese reports, the term rapid modular assembly was rendered poetically as Kikai no Mahu, or mechanical magic. To their minds, the Allies had achieved what seemed impossible, turning construction into a weapon of speed. In later testimonies, Japanese engineers admitted that this realization marked a turning point in how they understood the nature of modern warfare. Strength alone was not enough; it was the ability to reproduce strength endlessly and efficiently that decided victory. In Europe, as Allied columns advanced beyond the Rhine, Bailey bridges were now everywhere. They stretched across the Weser, the Elbe, and the Aller, built faster than maps could be updated. Engineers learned to improvise with astonishing speed, reinforcing trusses with scavenged rails, anchoring spans to tank hulls, even building double-decker configurations to handle traffic surges. Each bridge became a living organism of movement, evolving with the advance. By April 1945, the Bailey had become so embedded in the Allied operational mindset that engineers referred to their crossing teams as bridge battalions, each moving in tandem with frontline divisions. The manuals describing Bailey construction grew thicker with field notes, sketches, and refinements. In one such report preserved by the U.S. Army Corps of Engineers, a commander wrote, "The enemy blows bridges faster than we can count, but our bridge units replace them faster than they can retreat." That single observation captured the turning point perfectly. The Bailey Bridge had transformed the geography of war itself. Rivers were no longer barriers but brief pauses in the advance. After Germany's surrender in May 1945, engineers walking among the wreckage of the Rhine crossings found the surviving Baileys still standing, undamaged after thousands of vehicles had crossed. They were dismantled only after peace returned, the panels sent back to depots or repurposed for rebuilding Europe's shattered infrastructure. For Japan, those same months marked a quiet reckoning. Their officers, reviewing Germany's defeat, concluded that Allied superiority lay not only in numbers or weapons, but in systems, modular, repeatable, relentless systems. In post-war engineering schools, captured Allied manuals on the Bailey Bridge were studied alongside reports on radar and logistics. To those engineers, the bridge symbolized the new era that had dawned, an age where industrial organization and design mattered more than sheer manpower. It was not just a turning point in the war, but in the philosophy of engineering itself. The Bailey Bridge proved that the power to build, quickly, efficiently, anywhere, could be as decisive as the power to destroy. And that realization, born from the mud and fire of the Rhine, would echo far beyond 1945. When the war finally ended in 1945, the Bailey Bridge did not fade into obscurity with the sound of the last guns. Instead, it became one of the most valuable tools of peace. Across the scarred landscapes of Europe, where thousands of bridges had been reduced to rubble, the same portable structures that had carried tanks now carried relief supplies, civilians, and reconstruction materials. What had once been a weapon of war was repurposed into an instrument of recovery. In France, Belgium, and the Netherlands, British and American engineers worked alongside local crews to rebuild vital routes using leftover Bailey panels. The bridges proved as effective in peace as in combat. Their modularity allowed them to span bombed-out rivers and valleys quickly, restoring trade and transport long before permanent concrete bridges could be erected. The Allied control commissions distributed Bailey units to devastated regions as part of reconstruction aid, and even into the early 1950s, it was not unusual to see trucks, bicycles, and villagers crossing Bailey spans stamped with military serial numbers. In Britain, the Ministry of Works repurposed thousands of wartime panels for civilian infrastructure. In London, several temporary Bailey footbridges connected neighbourhoods divided by bomb craters and destroyed viaducts. In Italy, British engineers used them to restore rail lines through the Apennine Mountains. In Burma and India, the Bailey system became a lifeline for rebuilding transport networks washed away by monsoon floods. What had begun as an emergency military design evolved into a cornerstone of post-war reconstruction worldwide. Japan's interaction with the Bailey Bridge took on a more introspective form. After the country's surrender, the Allied occupation authorities permitted Japanese technical experts to examine a broad range of military technologies that had shaped the conflict, radar, logistics, and engineering systems among them. In late 1946, a delegation from the Japanese Ministry of Construction and the Army Engineering Bureau, now restructured for civilian purposes, was allowed to inspect Allied engineering documentation stored in Yokohama and Tokyo. Among those documents was a detailed technical manual for the Bailey Bridge, including drawings, stress diagrams, and assembly procedures. For the engineers who had once regarded the bridge as an enigma, it was a revelation. The post-war Japanese Technical Report, Evaluation of Allied Military Engineering Equipment, 1947, described the Bailey with striking admiration. The strength of the design lies not in complexity, but in the harmony between precision manufacture and human cooperation. It is a weapon that unites engineering with organization. Japanese engineers studying the Bailey system recognized its deeper implications. The bridge embodied a philosophy of standardization and interchangeability, principles that Japan would later adopt in its industrial revival. The idea that large, complex structures could be built from small, identical units resonated deeply with post-war Japan's emerging manufacturing ethos. The Bailey's logic, modular design, efficiency, and seamless coordination between man and machine would later echo in Japan's automotive industry, shipbuilding, and even railway engineering. By the early 1950s, Bailey-style bridges were appearing across Japan's rural and mountainous regions, helping restore transport routes destroyed during the war. The Public Works Research Institute used the Bailey's geometry as a teaching model for modular steel bridge design. Though many of these new structures were adapted to local needs, they retained the same pin-connected truss pattern that Donald Bailey had conceived a decade earlier. Some of those spans, upgraded and strengthened over time, still carry traffic today. In the broader world, the Bailey system became a quiet but enduring legacy of Allied cooperation. The U.S. Army continued to refine the design into the M2 treadway bridge and M3 floating bridge systems, while Britain and Canada developed heavier variants capable of carrying 70-ton tanks. During the Korean War, 1950 to 1953, Bailey bridges once again appeared on the front lines, bridging ravines and rivers under fire, just as they had in Normandy. The bridge's influence spread even further during the post-war decolonization period. Nations in Asia, Africa, and Latin America received surplus Bailey kits as part of infrastructure aid packages. In India, engineers used them to rebuild flood-damaged roads. In Nepal, they provided essential crossings through the Himalayas. In 1965, when floods destroyed hundreds of bridges in Malaysia, British and Australian forces airlifted Bailey components to restore vital links within days. It had become a universal symbol of resilience, a structure that could be assembled anywhere, by anyone, for any purpose. Back in Britain, Donald Bailey himself returned to a modest civilian life. He was knighted in 1946 for his contribution to the war effort, though he never considered himself a military hero. When asked about the bridge's success, he famously replied, "I merely designed something that worked." Yet his something had carried nations forward, through destruction and into recovery. For Japanese engineers reflecting on the war, the Bailey Bridge remained an enduring reminder of what had separated the Allied and Axis powers, not just technology, but systemization, the ability to integrate human labor, material, and design into a seamless whole. The post-war Japanese academic Hiroshi Takahashi, in his 1952 essay The Lessons of Allied Engineering, summarized it plainly. The Bailey Bridge taught us that civilization advances when the ordinary man can do extraordinary things through design. That lesson outlived the war itself. The panel's once marked War Department found new purpose across the world, spanning rivers, aiding farmers, connecting towns, and symbolizing the quiet triumph of design over destruction. Long after tanks and bombers had rusted away, the Bailey bridges remained, steadfast, functional, unpretentious, serving the peace they had helped to win. In the quiet years that followed World War II, the thunder of artillery gave way to the hum of reconstruction. Across Europe and Asia, rivers once crossed under fire now reflected the silhouettes of Bailey bridges, silent and steadfast. They stood not as monuments to destruction, but as enduring testaments to ingenuity. Where bombs had fallen, steel trusses rose in their place. And where armies had once fought to cross, farmers and school children now passed daily without knowing the history beneath their feet. The Bailey Bridge's story was never about heroism in the conventional sense. It was about a different kind of courage, the discipline to design something simple, and the faith to trust that simplicity under the most complex conditions imaginable. Donald Bailey's bridge asked nothing more of men than strength, coordination, and persistence. It did not promise glory. It promised reliability. And that, in the desperate arithmetic of war, proved more valuable than any weapon. When Japanese engineers called it mechanical magic, they were not speaking in superstition. They were naming something they could not yet replicate, a harmony between human labor and machine precision that the Allies had mastered. In that phrase lay both admiration and introspection. Japan had built beautiful things, railways, ships, towers, but the Bailey represented something else, design as doctrine, structure as philosophy. It was proof that victory was no longer the domain of those with the most soldiers or the largest guns, but of those who could think systematically, who could break complexity into manageable pieces and reassemble them at will. In the years after the war, that lesson quietly reshaped Japan's future. The same principles that defined the Bailey, modularity, interchangeability, and efficiency, became the backbone of Japanese manufacturing. The bridge that once humbled their engineers became a blueprint for their rebirth. From Toyota's production lines to the Shinkansen's maintenance systems, echoes of Bailey's logic lived on, the understanding that progress depends not on spectacle, but on precision and repeatability. For the Allies, the Bailey Bridge became part of a larger legacy, the proof that engineering could win wars and preserve peace alike. The U.S. Army Corps of Engineers still teaches its design today, and its descendants can be found in modern tactical bridging systems used by armies around the world. Yet beyond its military utility, the bridge remains a symbol of what the 20th century demanded from its engineers, not grandeur, but adaptability. If there is a single image that captures its meaning, it is not of tanks crossing under fire, but of a group of exhausted soldiers standing at dawn, watching their bridge stretch across a river that had been impassable only hours before. The water runs quietly beneath them. The panels are cold to the touch. The sun catches on the steel, and for a moment, they understand that they have done something far greater than survive a night's labor. They have created connection out of chaos. History often remembers the weapons that ended wars, the bombers, the battleships, the tanks. But the Bailey Bridge reminds us that sometimes, the true instruments of victory are the ones that build rather than destroy. Its legacy endures not in museums or ceremonies, but in the quiet crossings it still supports, in the simple act of a structure doing exactly what it was designed to do. When Sir Donald Bailey accepted his knighthood in 1946, he spoke softly, almost embarrassed by the attention. It was just a bridge, he said. But history proved otherwise. It was, and remains, the bridge that carried the modern world forward, one span, one panel, one quiet act of design at a time.